section 3, again, remember there are microphones in the room. Just raise your hand, and then otherwise you can also just shout loudly. The ceiling microphones will pick it up. Okay, Thomas, thanks for doing it. Over to you.
Okay, great. Yeah, I also wanted to say thank you to the organizers, the other organizers, for putting this together, and also thank you to Simon for sort of setting this up and hosting it and being willing to tolerate people like me that are doing this remotely. I certainly do hope to get to the Institute in February once things settle down a little bit. Okay, so the talk here has 2 parts, but I'm not going to get to the second part. So I'm going to talk about single-world intervention graphs. This is a framework for relating graphs and counterfactuals or potential outcomes via node splitting. And I'll show some simple examples, give you a general procedure, and we'll then talk about adjustment for confounding. And then connecting back to what Spencer presented on Tuesday, I'll then show how using potential outcomes, we can simplify the do calculus and also reformulate it. But and then I'll give us an illustration deriving the front door criterion, which is also talked about on Tuesday via the potential outcome calculus, PO-calculus as we call it, and I'll talk about sequentially randomized experiments. Okay. So up to this point, this is just again review. We had the graph on the left, which represents no confounding. The graph on the right is confounding. This is, remember, the convention that when we draw a DAG and we interpret it causally, we're sort of obliged to always include hidden variables if hidden variables are present. And then this approach originates with work of Sewell Wright in the 1920s, geneticist. And yeah, this is terminology that you already know that we.
Could I ask you to make your slides as large as possible?
Okay.
Thanks. Thanks.
So I'm not going to make them quite that large. A little bit too large, I think. Okay, is that better?
Yeah.
Okay. So the key thing is that if I have this graph on the left that represents where there's no confounding variable between x and y, this represents the idea that there's no confounding. As you saw, we have this associated factorization, which is trivial. And in the absence of confounding, the causal model asserts, and here I'm writing the assertion both in terms of potential outcomes and in terms of do that we saw on Tuesday. It's saying that the distribution over y, if everyone were to get, were forced to take the value x, is the same as the conditional distribution for y given x equals x, which is the same as, so these are 2 ways of just saying the distribution where we intervene to set x to x. This is the potential outcome way of writing it. This is the do calculus way of writing it. And then the fact that there's no confounding says that these things, which are the same object, is equal to the conditional distribution of y given x. And this is basically what we saw back in the first lecture this morning, that the average causal effect is identified under this model. So a question that you might ask is, well, how does this relate to the potential outcome approach? I mean, I've sort of shown you this over here, so I'm already relating it a little bit, but in particular, you'll recall, hopefully, that when I talked about the absence of confounding, we talked in terms of these independencies. We talked about treatment being independent of the potential outcomes. So this is in the potential outcome terminology, this would be called treatment assignment is ignorable or weakly ignorable. And then confounding corresponded to at least one of these independencies not holding. Okay? And so if you sort of followed the discussion on Tuesday, you'll have realized that graphs are this very powerful representation for dealing with for reading off independencies and conditional independencies. And they also have a causal interpretation. And so here, the potential outcome framework characterizes the absence of confounding precisely in terms of these, or can be thought of as characterizing it precisely in terms of these independencies. And we've got a graph here. So the natural question is, okay, this is a causal graph. Here we've got an independence. That independence captures this absence of confounding. Can I read this off from the graph? That seems like a very reasonable thing to think that one might be able to do. But there's a sort of problem, which is that if you remember anything about deseparation and deconnection from Tuesday, you'll be aware that you can't really read something off the graph if the variable doesn't appear on the graph. Okay? And so we have the what we could call the elephant in the room here, that doesn't matter how long you stare at this graph, there are no potential outcome variables on the graph, so there's no way you're going to get to read this off. So this has sometimes been used, that there are certain people who will remain nameless who have said that these graphs couldn't possibly be causal because we know that causality in at least since Neyman is captured in terms of potential outcomes, and there are no potential outcomes on the graph, therefore these are not causal. I'm not advocating for that. I'm going to show that I think that's overly simplistic and misses the point, but it has been argued. Okay, so what are we going to do? We're going to show a way of transforming the graph. We're going to add some additional semantics onto the graph via a notion of splitting a node that will then allow us to read off the independence that we naturally associate with the absence of confounding from the graph directly, just using deseparation. So here's the idea. We start off with this graph over here on the left. This is the associated factorization. The tildes here are just because I'm going to want to refer to more than one level of X. So therefore, I'm using tilde here. And now I'm going to split X, this random node. This is the graphical operation. I'm going to split it into two pieces. This piece X, which is random. And then there's going to be a fixed piece where X is equal to 0. And then everything that's downstream of this fixed piece, in particular this Y, is going to then become a potential outcome. And so now we can now read from this graph over here on the left, we can read the independence, because X here, this is a separate node. So the purpose in splitting will become clear later, but the purpose in splitting is partly just so that I can look at the graph on the left and easily work out what was the original graph from which it was obtained. But we're just going to think about the random nodes just as if they were random nodes in an ordinary DAG. So here's X, here's Y of X equals 0. If you remember anything about deconnection, you'll be aware there has to be a path between these two. There is no path, so therefore we read, therefore X and this guy are deseparated, so we can read off this marginal independence. Okay. So we can also associate, we associated with DAGs of factorization. The random variables we've got over here are X and Y of X equals 0. So the factorization we're going to get is just going to be this. This is just the simple factorization that that we will get. Okay, so X and Y of X equals 0 are, there's no edge between these two, so we get this very simple factorization. And then you might say, well, that's all very well. You've constructed this new graph. You've got this new variable here. How is that connected to the original graph and the original distribution that we started out with? Okay. And the way that we're going to do that is we're going to say that the distribution of Y of X equals 0, minus the distribution of Y of X equals 0, we'll obtain from the distribution of Y given X in the original graph by just taking a conditional distribution of Y given X equals 0 in the original graph. Okay, so essentially we've built a new graph by splitting a node in this graph, and we built a new distribution by sort of repurposing, by taking the terms that were in our original factorization to the observed distribution. We just copied that term directly over, and then the second term here we obtained by now setting X to 0 in this term in the factorization, and that then gives us our new factorization associated with a new graph. And so sometimes I'll refer to the first there are two things we did here. We first just sort of posited a new distribution over X and this potential outcome. And we said it factorized according to the new graph. So we'll call that factorization. And then the second thing we did was we linked this new term in our new factorization back to a term in the original factorization, and that we could call that was sometimes called modularity. So the thing I want you to think about is what I'm presenting here today is like a bridge linking causal graphs to potential outcomes. And this, because it's a bridge, it can be crossed in either way. The way I'm presenting it to you at the moment is in the way whereby I've got a DAG and I'm interpreting it causally. I'm sort of comfortable doing that. But now maybe I go and I want to communicate with biostatisticians who think in terms of potential outcomes, and I want to be able to translate the assumptions that are encoded in my causal graph into assumptions in terms of potential outcomes. And I can do that by crossing a bridge from causal DAGs to potential outcomes by splitting, and then I can use my familiar tools of deseparation and then this factorization to then make assertions about potential outcomes that sort of biostatisticians who work with potential outcomes can then use. But we could also go back in the other direction. If you're someone that is familiar with potential outcomes already, and I present this framework to you, then you might look at this equation here, and you might say, okay, wait a second, that equation looks to me like something that would follow from the factorization from this independence plus consistency. And you would also be completely right about that. So if I start off with the marginal here, if I start off with this marginal distribution, then well, because the graph asserts that this marginal distribution, this random variable is independent of X, then I can then, then this term is equal to this term. And then I could then use consistency. I could then use consistency to then get this to this form. Okay, so there's a question from Leonard here saying, is X equals 0 a variable? And so just for the moment, I want to say no. Okay, so at the moment, I'm thinking about this as just something I have in the graph that I'm putting in here. It's really there so that I know why it is that these subsequent variables are labeled with this potential outcome y of X equals 0. Give me a few more slides and I'll start, we will start doing something with this particular thing at the moment. But for the moment, you can just think about this as, this is just a little label that I've got in here to remind me how I came up with this distribution over the random nodes that are here. We will later obviously do things with this red node, but for now, just don't focus on this red node for now. We'll come back to it. Okay, so here I'm doing, we set X to 0, we got some results out. We could obviously split and have X equal to 1. That would then give us this graph, okay, where we could now read off this independence. And we would then get a new factorization over the variables that are in this new graph. These two, it factors in this way. And we then we will get this additional assumption that would say, well, I'm going to build this piece, this term, from the original factorization in this way. Okay? Or again, if you are a potential outcomes person, you could take the distribution over if you're a potential outcomes person, the basic objects for you are X and these potential outcomes for Y. And then I could use this independence and consistency to then get me this equality. That's if you're crossing the bridge. If you wake up in the morning and the things you see are potential outcomes, but you then want to sort of understand how you could translate those back into causal graphs. Okay, so I did it with X equals 0. I did it with X equals 1. I'm not going to insist that you construct a separate graph for every value of X. That would be very time consuming, especially if X took infinitely many values. But there is a point here, and the reason we're doing this, so the new graph that we were constructing, this one where we split, we're going to call a SingleWorld Intervention graph. And the reason for that term SingleWorld, I'm now going to explain to you. So there were two graphs I showed you. The first one I'm calling G of X0. That was representing this distribution. The second one was representing this distribution. And the key point that we saw is that under no confounding, these marginal distributions are identified from the joint distribution over X and Y. So in contrast,
sound just broke up.
Sorry.
Okay, need to be back.
Yes, that was my iPad getting above itself, basically. I don't know why.
That was the last that we heard.
Sorry, yes, in contrast, in contrast, if you're a graphical person, is that where I stopped?
Yeah.
If you're a graphical person, you might say, well, wait a second, we've got these three random variables, x, y of x0, y of x1. Graphs are great. Why don't I just try to use a graph to represent the joint distribution over these random variables? And that is
Your sound is breaking up again.
Sorry, it's doing it again.
Yeah. Where's that?
Just a second. Okay, are you hearing me now?
Yes, this is good.
Okay, I'm gonna kill Bluetooth here. Okay, I think we're kept the iPods at the gate out. Okay, AirPods. Okay, so so basically, you might think to yourself, well, wait a second, why don't I just build a graph for this whole joint distribution? And that is an approach that Perl took with twin networks. But there are some problems with that. And one of the main problems is that it's very hard, we'll see, it's very hard to do that in a way without introducing additional assumptions. And some of those assumptions are things that could not be tested via any randomized experiment. And we'll see that, in fact, that approach quickly leads to sort of super exponentially many assumptions that are not really required. And yeah, I'll talk about that a little bit more. But essentially, the idea is we're going to construct two different graphs, one representing this margin, one representing this margin, one representing this margin. We're still thinking that there is an underlying joint distribution, but we're not going to use a graph for that underlying joint distribution because we want to use the graphs to make the kind of assumptions that we could test via a randomized experiment. And if we put a joint distribution, if we put a graph over all of these variables, we will very quickly start making additional assumptions. So in particular, I had one graph that represented this independence, one graph that represented this independence. If I had put them all on the same graph, all three variables on the same graph, then you know that if x is deseparated from this and x is deseparated from that, then x will be deseparated from both of them. So as a sort of simple example, we will be forced to have this joint independence. And you might say to yourself, well, okay, but big deal, this is sort of weak ignorability, this is strong ignorability. If I randomized x, then I would expect strong ignorability to hold. That's a very reasonable point. It does seem a bit pedantic in this context, but once we talk about examples as more variables and mediation, we'll see it's very easy to very quickly start making what we'll call cross-world independence assumptions. And the framework I'm presenting is very carefully set up to try to avoid making cross-world independence assumptions that could not be checked via a randomized experiment. Okay, so yes, had we tried to construct a single graph, it would have been impossible to have these two independences and not this one, at least if we were using deseparation. We might be able to come up with some more sophisticated semantics, but at least with semantics that are currently known for graphs, we couldn't have done that. And this is where the word single world comes from, because here we're not constructing a graph that contains both of these potential outcomes. Okay, so back to the question that was raised in the chat, which is about the nature of this fixed node. Obviously, I'm not really proposing that if X takes 1,000 values, you should construct 1,000 different graphs. You can certainly represent all of them using this template. But the key thing is when we look at this template, I want you to think about this as a sort of graph valued function rather than a graph. So the idea is you come to me with a particular value of particular value of X you're interested in. I plug that in, and then this thing then gives you out a graph representing the joint over X and the potential outcome Y of X set to that specific value. So each instantiation of the template is going to represent a different margin. Okay, and so just a sort of aside here, you might think to yourself, well, you were saying this was connected to testability, but this graph is representing a situation where I get to see the natural value of X. It's representing a joint over X and Y of little x. That's what kind of world does this represent where, we could know someone's natural value of X, we could know the value of X that they would choose, but then we could also intervene to set X to a specific value and then see their potential outcome. So for example, how could it be that we could both see that someone would naturally choose to take treatment if left to their own devices, but also find out what would happen to them in the absence of treatment? And so here we come to the point where it helps that one of my co-authors is an MD and came up with this hypothetical thought experiment where essentially so consider an experiment. This is a thought experiment. I wish to stress that, but where we simply monitor a patient through their Facebook feed or whatever camera is pointing at them at the current time. And then at the moment where we see them take the drug and swallow it, we instantly intervene, a little bit like the swoop in like in Minority Report, and we then administer a safe emetic that causes the pill to be regurgitated before any of the drug can enter the bloodstream. So the idea is that we can see that the person would have chosen to take the drug, but we can intervene before there are any causal effects of them having taken that drug. And since we're assuming the emetic has no side effects, the patient's recorded outcome is then going to be Y of X equals 0. Okay, so this is just a thought experiment, but it's helpful, I think, because it ties into this idea of splitting. The idea of splitting is that we're imagining an instant in time where we get to see what the natural value of treatment would be, and then we intervene. Okay, so let's look at a slightly harder inferential problem. So let's consider this graph. So here I've got two treatments, A and B, and then A influences A. We have a response Z and then a response Y. The response Z just comes after A. The response Y comes after Z and B. And then we have a hidden variable that confounds Z and B. So the question here is, does this graph imply this independence? So now I'm suddenly telling you about a graph where I've got two treatments, but I can do that. So I'm giving you an example of a more complicated case, and then I'm going to give you the full algorithm, but I think the example helps to explain, to give you the idea of the algorithm. So what are we doing here? We've split A, we've split B, and then everything that's downstream from the fixed part of A gets labeled with an A, and everything that's downstream from the fixed part of B gets labeled with a B. Okay, so we've now got a graph representing a joint distribution over A, Z of A, H, B of A, Y of AB. Okay. And now we can use our deseparation toolkit that was explained on Tuesday to read off from here, okay, Y of AB, is that deseparated from B of A given Z of A and A? Well, there are two paths from here to here. There's this path and there's this path. On both of those paths, Z of A is a non-collider. So yes, Y of AB and B of A are deseparated given Z of A. We didn't actually have to condition on A. That's in there for sort of historical reasons that I can go into, but you can see that we can easily read off from this graph that this independence holds. Okay. So let me tell you the general strategy here. So the general strategy is that I'm going to give you a graph and a set of treatment vertices to be intervened on. And then we're going to form the graph G of A in two steps. In the first step, each treatment node is going to be split. So in the previous case, that was A and B. We split those, and we're going to split it into a random half and a fixed half. then the random half will inherit all the edges directed into A in G, and the fixed half will inherit all the edges directed out of A in the original graph. Okay, so the fixed part gets the sort of child edges, and the random half gets the parent edges. And then in the simplest scheme, we just relabel everything that is downstream of this fixed node in the graph after we make the splits, gets labeled with that fixed node. So here we get this. So everything that's downstream, this is a slightly busy figure, but this is just a schematic to show you we first do all the splits, and then everything that's downstream of the fixed node A gets labeled with little a. I'm also going to describe some other labeling schemes. This is a labeling scheme that I call ancestral. We will describe some other labeling schemes shortly, but this is the simplest one. And it's also intuitive. It's telling you that essentially that these are the variables that you can think might be affected by setting A to a specific value. Okay. So here's a summary. So here, how we can add cross the bridge sort of from DAGs to counterfactual distributions. We start off with a graph G and an observed distribution P of V. We form the new SWIG in the way that was described by node splitting and then labeling. That gives us a counterfactual distribution of P of V of A. And note that under the minimal or ancestral labeling I just showed, not all the variables in the graph will be labeled with the full set of things we intervened on, right? So we saw that already here. This guy is labeled with A and B, but these guys are not labeled with both A and B, and indeed this guy is not labeled with anything. Same with H. Okay, and we assume, so basically the model assumes factorization of the counterfactual variables. And we have this modularity assumption that says essentially the conditional density associated with a random node in the new graph is just the conditional density associated with the corresponding node in the original graph after substituting in the fixed value for any treatment that was a parent of Y. Just directly analogous to the previous example we saw, the simple two-node example we saw.
Clarification question is, does this SWIG construction only work for atomic or fixed interventions, or does it work for more general interventions as well?
So the construction I'm presenting here is just for thinking about static interventions, but the machinery can also work for dealing with dynamic regimes, but it gets more complicated, and yeah, I won't get into that in this lecture. But the splitting idea that we've got here, we should think about that as static interventions. So for those of you that are wondering about that question, the idea is you could imagine, you know, there's often interest in thinking about a treatment regime where, you know, it's not that we just give everyone a treatment at every point in time, but maybe we come up with a rule that tells us to treat people based on how they're responding to treatment initially. And so in that case, you have sort of dynamic counterfactuals with a regime, with a dynamic regime. So the framework has been designed so that you can accommodate those, and indeed also accommodate dynamic regimes that depend on the natural value that a variable would take. So for example, you know, something like a regime where we ask people to do 10 minutes of exercise per day, or however much exercise they would do usually if that's more than 10 minutes per day. So we're not telling people if they're already doing 20 minutes of exercise per day that they should only do 10 minutes. We're going to tell them that if they're doing less than 10 minutes per day, we want them to get up to 10 minutes per day. But if they're doing more than 10 minutes per day, then they should go on doing what they were doing, or, you know, income supplement or something like that. Income supplement program would be another example. Okay, so having set this up, we can now think about, we can apply deseparation to the graph, and I'm going to tell you that in 2 stages. So the first part, the first way, the key thing, the red nodes, the fixed nodes are going to be relevant here. And the key thing to remember is that we're never going to allow a red node to be a non-endpoint node on a path. So any path that goes through a red node is always blocked. It doesn't matter, so we just don't ever consider paths that have red fixed nodes on them unless it's as one endpoint. Okay? But for now, on this slide, I'm going to think about paths that start at a random node, end at a random node, and don't pass through any fixed nodes. Okay? So if it's a fixed node and it's not, and it's in the middle of a path, it's a non-endpoint, then that path is automatically blocked. Okay, so so our definition of deseparation is identical to the definition that we had before, except for the fact that we never condition on fixed nodes and we never allow paths that go through fixed nodes. Okay? So for the purpose, so in this slide, I'm talking about deseparation as being a relation among three subsets of random variables that occur in the SWIG. And so, yeah, so I think a key point that maybe I skipped over, not sure. Yes, a key point I wanted to make on the previous slide is that it follows from this factorization and modularity assumption. If we observe the joint distribution over the variables in the original graph, then whatever SWIG we construct, the distribution over the counterfactual random variables that occur in that SWIG is identified. So that all the graphs we're constructing correspond to distributions over counterfactuals that are identified if given that we observe the joint distribution over all the initial random, all the variables in the original graph. Okay, so this is just saying what was implicit in the example that I showed you. If I give you a SWIG and you look at three subsets of random nodes in that SWIG and you say, okay, I'm ignoring paths that go through red fixed nodes, just ignore them completely, and I have deseparation, then we will have conditional independence in the corresponding counterfactual distribution. Okay, any questions at this point? Maybe I should do another, let me do a couple more examples.
Up in the room.
Okay. Okay, so let's talk about adjustment for confounding. So this was already described. So I apologize that the next hour and a half, they're going to be the front door and back door are going to be sort of gone over several times. So buckle up. We're going to do them both twice. But okay, so here's the graph we think of as being a situation where if we're interested in the effect of X on Y, then we can get that by using the backdoor formula, adjusting for L. Okay, so here we start off with this graph, we split, we get to this graph, and then we can read directly from this graph that X and Y of X are conditionally independent given L. Okay, and this if you have a econometrician or biostatistician friend who doesn't use graphs, but does causal inference, they will recognize this. They'll say, oh, that's conditional ignorability. Okay, and so they'll see that. So you'll be able to explain that this graph implies this condition, which is the condition that is sort of understood in potential outcome terms as being the situation where we can use the backdoor formula. Okay? And so you can sort of see that. Here's a little proof, right? So here's I'm interested in knowing this. This is the distribution over Y when I intervene to set X to X tilde. This is total probability. Then the independence, because I've got this conditional independence, I can add X here in this term because of this conditional independence. And now I use consistency to get from here to here. And now I've got my identifying formula. Okay, we can, if your friend says, oh, but wait a second, what happens if there was a confounder, an unmeasured confounder between L and X? Well, as long as it was just between L and X, then you can work out, yep, that conditional independence is going to continue to hold, because now, although we've got two paths between Y of X and X, L is a non-collider on both those paths. So when I condition on L, both of those paths are blocked. So we're going to get this conditional independence. And so, yep, we can still use the backdoor formula in that graph. Or if it goes this way around. But we can also see that if we were unlucky enough to have a hidden variable between L and X and a hidden variable between L and Y, then we would be out of luck, because at that point, the path Y, H, L up to the other hidden variable and down to X, conditional on L, would deconnect. Right? So we can see that, in particular, we can see that that if we had two confounders, then we could not use backdoor adjustment. And even more strikingly, and this is sort of contrary to things that you might read in some econometrics textbooks, you can also see that if I had a confounder between L and Y and an independent confounder between L and X, and I didn't have these two edges. You see, let me just draw this. Okay, so if I had a graph that was X, L, Y, H1, H2, right, which would give me the swig X, little x, Y of X, H1, H2, L, right, we would see that this graph would give us that X is independent of Y of X, but X is not independent of Y of X given L. And so this is, I think this is very important. This is one of the main contributions of the graphical approach, is to be aware that this type of situation can arise, because there are some, I think it's older books, but there are some econometrics books you can read that will say that essentially there's no such, there is omitted variable bias. So omitted variable bias arises when you have, you know, X is not independent of Y of X, but this independence holds. Sorry, I forgot to put a cross through there. But those books will say that it cannot be the case that you would have treatment was unconfounded marginally, but then when you condition on a variable L that could have been pre-treatment, you end up losing ignorability. So I think, yeah, this is the fact that this can arise is really important to be aware of. And from my perspective, this also motivates graph learning algorithms, because essentially you realize that there isn't a kind of Whiggish, inexorable progress to controlling for confounding. You realize that you could be unlucky, you could have a set of confounders that was sufficient to control for confounding, and then you add in another variable, and suddenly, you know, unbeknownst to you, by adding in another variable, you've now induced confounding, and then maybe you add in some more variables and you stop having confounding, and then you add in some more, and then you induce confounding again. Whereas the sort of the false theorem that says that there's omitted variable bias, but there's no such thing as variable inclusion bias, it sort of gives you this idea of the inexorable march of progress, that I just keep on adding in more and more and more confounders, and I'm never going to sort of take a step backwards. Okay, I want to say a word about labeling. So up till now, we just had this scheme. We started off with this graph. If I split on A and B, and I label, then I then get this graph. There are situations where we want to use other labeling schemes. So one labeling scheme would be, for example, that I just label that when I split, everything that comes temporarily after a given node gets labeled with that. So here, for example, even though C is not downstream from A after we split B, not downstream from this fixed node, I'm still labeling it with an A here. And in this particular case here I've just got uniform labeling, where I'm just labeling everything with the fixed nodes. Okay, so the temporal order scheme, so I'm not going to be able to go into a lot of detail on this, but basically the temporal scheme, the idea, this is motivated by the idea that we might sometimes want to have missing edges in our graph correspond to the absence of a causal effect at the population level without assuming that it's absent at the individual level. Okay, so remember this morning in the simplest possible case where we were looking at a treatment and a response, I made this point that if the individual causal effect is 0, what does that mean? It means there's no one who is helped and no one who is hurt. If the individual causal effect is 0, that means that the average causal effect will be 0. So the proportion of people of type helped and hurt will be equal. But if the only data that I have access to is from a randomized experiment, all I can do inference on, the only thing I can identify is the average causal effect. And so if I've got some reason to think that an edge is missing, but that the reason I think that the edge is missing is because it came from a randomized experiment, then I might not want to assume that I know that there's no effect at the individual level. Okay, and so I can use a graph like this to represent the idea that I know that sort of A has no effect on C after intervening on B on average, but I'm not yet I'm not asserting that that's holding at the individual level. Of course, I could adopt other inferential principles like faithfulness or various Bayesian arguments whereby I would say, but how likely is it that things perfectly balance out so that effect is 0 at the population level without it being 0 at the individual level? I could certainly adopt those things, but there are times where it's useful to not. There are times where we want to be very precise and where we want to see exactly what are exactly what is needed for a given inference, and so for that purpose, this is useful. So this kind of scheme. So this kind of scheme can look a little bit nutty because it's saying, for example, that here this potential outcome for A, we're allowing it to potentially depend on B, even though B is something that takes place later in the future. So it seems as if we're violating the arrow of time here. One reason for this scheme is just there are times where you want to be able to unambiguously, if I've got several different swigs I'm talking about, and in some of them I'm splitting different subsets of variables, it's just useful to have a scheme that lets me talk about which variable is in which graph, right? Whereas if I look at this, if I tell you I'm looking at B of A, you don't know whether or not that's B of A in the graph where I split A or B of A in the graph where I split A and B. So it's just useful to have this uniform labeling scheme for certain purposes, such as the one I'm about to show you. Okay, so I'm going to go through this next part, a couple of the next slides, sort of assuming that you were here on Tuesday and saw Spencer's great presentation of the do calculus. But before I do that, I have to give you one more definition. So up to now, we've talked about deconnection or deseparation between random nodes. But there's also some utility for thinking about the absence of deconnecting paths where one endpoint is a fixed node. So we'll say that a path on which one endpoint is a fixed node, that it can deconnect to a random node if it satisfies the usual conditions on colliders and non-colliders. So that means, as before, all of the colliders and non-colliders must be random. We're not allowing any nodes on the path except the endpoint to be fixed, and we're having the usual conditions on those variables. Question? Okay, so if a fixed node D is d-separated from a node B of AD given C of AD, then it will turn out that the conditional distribution for B given C does not depend on the value to which D is fixed. So in other words, the conditional distribution of B given C after intervening on A and D does not depend on the value assigned to D. So this is some more information that we're able to read off from the swig. Okay, do calculus. So as you probably may know, or if not, you saw on Tuesday, Pearl formulated a set of 3 rules that allow 3 transformations. So one says, when is it the case that I can, if I've the distribution of y when I see z and see w and do x, when is it the case that seeing z doesn't change that distribution? And here, this is just sort of helpful practice to translate this into potential outcomes. This is what that statement looks like in terms of potential outcomes, right? So we do x, so everything is labeled with x, and then we're just saying when can I drop the random variable z there. The second one was about when could I interchange observation and intervention. So here we go from this to this. We basically, what changes when we cross here is that we get, we go from here having seeing z to here intervening on z. So in potential outcome language, it just corresponds to this equality. So you can see it on the left, we conditioned on z of x. On the right, we've now intervened on z. So we get w, everything is labeled with little z here. And we could remove interventions, right? So in do language, we just get to drop the do. Potential outcome language, we just drop the z. Okay, you'll also remember that Pearl gave some rules for reading these things off, and those corresponded to checking these separations in various graphs. And there was a graph, this graph for the first rule, this graph for the second rule, and then this graph, which was a bit complicated, to be honest, for the third rule. So the good news is if you didn't totally take this all on board, there's no harm, because we're going to simplify this so that you don't need to, you can do everything just with SWIGs, and you don't need to remember these complicated definitions. Okay, so here are the rules. So the first one is sort of fairly easy. We just say, well, when are these two things equal? Well, that's when y of x is deseparated from z of x given w of x in the SWIG. It's just, this is just conditional independence in the SWIG. Second one is, when is it the case that I can switch from intervention to observation? And that holds when y of xz is deseparated from z of xz given w of xz. Okay. So here I should say, in these rules, I'm using the uniform labeling, where I'm labeling everything precisely so that you can tell which SWIG we're talking about. Okay, so okay, and you could also, just as an aside, you could also derive this actually from this first rule and consistency. If you're a counterfactualist and are familiar with consistency, then you can sort of read this off. But you can also think about this as an instance of ignorability. Ignorability plus consistency. And then the even better news is that the third rule, we're going to replace the third rule with a much simpler rule, which just said if z has no directed path to y of xz in g of xz, then these two distributions are the same. So that then dropping z is not going to change the Meisel distribution of y. Okay, so this still may look a little bit cluttered because we've got x all the way through. So everything here was assuming that in the background we were intervening on x. And because really this is very simple, so Alexander has a question. I think I'm going to take that at the end because I've only got 10 minutes left. So basically, in terms of here all the way through, we're intervening on x. So just to show you, to sort of reduce this down to make absolutely clear what's going on, we're just going to consider the case where we suppress the interventions on x. This is what I call the TLDR version. So the rule 1 just corresponds to deseparation. Rule 2 corresponds to deseparation of y of z from z of z, the natural value of z, given w of z in the graph where I intervene on z. So this is just generalized ignorability. And then the last one is simply causal relevance. Okay, so the reformulated version is just 3 things: deseparation, ignorability, or equivalently this independence, and interventions only affect causal descendants. Okay, I think that's, yeah, so I think that's somewhat simpler than was the original formulation. And I should say, yes, this is joint work with Dan Malinsky and Ilya, with also some inspiration from Jamie. Okay, so here, yeah, so let's just show how we can derive the front door. Okay, so this is the graph, front door graph. I think, yeah, these are maybe labeled. They were previously being called, Spencer had different names for the variables, but it's the same graph. Okay, so I want to know P of Y of A. So just law of total probability lets me express that way. And then now I can look at the graph where I intervene on A. Look at this graph, and I can see here, okay, I can see that M of A is d-separated from A given the empty set. So therefore, I can use rule 2 to replace this term with this term. Then I can now look at this guy, and I can say Y of A. I'm looking at the graph G of AM, and I can see that Y of AM is d-separated from M of A in the graph where I intervene on A and M. So therefore, that tells me that this guy, this is my rule 2, this guy is equal to this guy. So I get to do that replacement. Then now looking at this graph, I can now see that I can see that in the graph where I've intervened on A and M, that there's no directed path from A to Y of AM, so I can just drop A from this. So I get to this term. And then finally, I can, so now I'm pulling the P of MA out to the front, and I'm using law of total probability again to re-express this term like this, just law of total probability. And then finally, I can use the fact that A is that in the graph where I so Y of M is d-separated from M given A, so consequently I can now go from here to here. So this is just using rule 2. Okay, so this slide is in here in case there are people that you went through the derivation, you carefully memorized this on Tuesday. You're thinking to yourself, well, this seems like how could it be that we could simplify this? The reason it's possible to simplify this is that, in fact, many instances that Pearl's rule here actually split Z into 2 parts: Zs that are ancestors of W and Zs that aren't ancestors of W. And it turns out that we can, it turns out that any Z that is an ancestor of W, when the condition that holds in Pearl's rule applies, then it's possible to use rules 1 and 2 to already remove those that part of any part of Z that is an ancestor of W in the graph where we've split on X. This is a typo. It should be G sub X bar here in these cases. Okay, so that's why it's possible to simplify this, because actually a lot of Z can already be removed using rule 1 and rule 2. And then the remaining cases, we're just left with variables in Z that are not ancestors of W, which then makes the condition much simpler. Okay. Okay, so just the last little bit here, I'm going to talk about multiple treatments. Just to give another example of this. So this is a graph. There was a question asked yesterday, which was, can you give us a concrete example where we would know that a particular graph holds? And so this is this is sort of the sequentially randomized trial example. So the idea is I've got two treatments, A and C. The first treatment is randomized. The second treatment is randomized conditional on the observed history, A and B. But B and D are responses, and they may be confounded by the patient's underlying health status. Okay, so the great thing about this graph is we could make it hold by design. If we randomly assigned A, observe people how they respond B, then randomly assign C based on their observed history. So the probability that they get C may depend on their observed history. We could make this graph hold by design. Okay? And now what we want to do is, given that we did this experiment, we would like to know the distribution over D when we intervene on A and C. Okay, so the old results of Jamie's say that if these two independencies hold, then we can use this expression, an instance of the G formula, to identify this. Okay? I'm going to give you, in the last lecture, I'm going to show you how to derive this. But for now, just suppose that you had your friendly epidemiologist who said, I learned in Epi 101 that we can solve this problem if these independencies hold. But somehow they skipped the lectures on SWIGs in Epi 101. So the question is, do these independencies hold? Well, we can just split, and we can then read off that A is independent of A. Obviously doesn't have any nodes into it, so obviously this is deseparated from this. And then it just remains to check, is this independent of this given this and this? And the only thing we have to remember is that although it might look like there's a path through A, this is a fixed node, and we never allow paths that go through fixed nodes. So we only have to worry about paths through B of A, but if we're conditioning on B of A, then B of A is a collider. And so this deseparation holds, and we can apply the formula. So Pearl has a twin network approach. Don't have time to talk about this in great detail, but the twin network approach would involve drawing this graph in order to check those conditions. And this also corresponds to stronger assumptions. It basically corresponds to making additional counterfactual independence assumptions that are cross-world. And so I'm going to skip that. I'm just going to end up by saying, I want to make a quick comment about relating this to counterfactuals and structural equations, because there was a sort of deep comment that Spencer made on Tuesday, where he said the structural causal models, and then we're looking at their shadow, causal Bayesian network shadow. And so this is what a structural equation model looks like. Each variable is expressed as a function, deterministic function of its parents plus an error term. But we could rewrite that in terms of potential outcomes like this. We just sort of, if we just put we can think of each equation as essentially just specifying the potential outcomes, and then we get our observed variables back by sort of recursively substituting. So we get our random value of X, and then we stick it into here, that gives the value of M. Then we stick those into here, that gives the value of Y. Okay, so we can map backwards and forwards between structural equations and potential outcomes. So Pearl has often said that structural equation models and potential outcomes are equivalent theories. This should say structural equation models and potential outcomes are equivalent theories. They are. That's true, but the issue is that usually when people put down non-parametric structural equation models, they tend to assume that errors are independent. Okay, so if you say that there's no confounding, then people will typically make the error terms independent. And the point is that assumption of independence of errors corresponds to making a lot of cross-world and hence untestable counterfactual independence assumptions. So sort of here's the simplest case: Z, M, Y. If everything's binary, we would have these 7 counterfactual random variables. Structural causal model assumes cross-world independencies, typically. I mean, assuming you don't put in bidirected edges. If you just draw this graph without bidirected edges, it's then assuming that this is independent of both of these, and both of these are independent of all of these. And so that means that we're putting in place a lot of independencies. We can quantify exactly how many independencies are being made. So if you made no assumptions, then we've got 7 random variables. So we've got a distribution of dimension 127. The SWIG defines a model of dimension 113. The non-parametric structural equation model with independent areas defines a model of dimension 19. So there are 94 the difference between these two is 94. So 94 additional counterfactual independence restrictions that are being made by this model, the structural causal model. And, you know, if you want to think in terms of computational complexity, this grows pretty quickly. Okay? So once we're up to 4 variables, the number of additional testable, untestable independence constraints, the extra independence constraints that are being made by the structural causal model is in, you know, 32,000. So yeah, so summarizing the structural causal model independent error assumption, it can't in general be checked by a randomized experiment on the variables in the graph. I think that's a problem because the whole point about the whole renaissance in causal literature in the 20th century was sort of where we got away from Kant was when people started thinking about cause and effect in terms of experiments that could be carried out. That's sort of gone when we do this. Yeah, people might say, but hold on, don't you do causal discovery and doesn't that require faithfulness? Yes, it does, but faithfulness is a bet. It's a Bayesian assumption that if we see a constraint, it didn't arise due to chance. It's a bet. It's not metaphysics. The problem is that in Pearl's framework, if you put down a non-parametric structural equation model, it often seems as if the act of just writing down a DAG licenses making these untestable assumptions. Okay, I've run over time, but I'll stop here.
Thank you. Just in the chat, there were 2 questions actually that both were high-level questions asking, I think, about whether there is a preference for particular tasks when you should use the potential outcome framework versus other tasks where the graphical model framework might be better.
Okay, so I think you know, this is like the question: how many foreign languages should you know, or how many languages should you be able to speak? Right? I think you know, I have a fairly unambiguous answer there that the more you know, the better it is. There are lots of things that it's very hard to express in terms of purely in terms of in any one language. Okay? I mean, if we want at a high level, if you're trying to think in terms of causal, so what are the downsides of potential outcomes? As I said, going back to this, people spent a long time working with potential outcomes, and there were a priori statements which sort of ruled out that said this was impossible a priori. It was impossible to have, you know, no confounding marginally, but confounding when you conditioned on L. So that shows there's a blind spot because we can easily describe a scenario where that arises. You know, I don't think this is a scenario that arises very often, but logically, it's a perfectly valid scenario. We could easily imagine this arising. So potential outcomes have their blind spots. On the other hand, there are lots of distinctions that can be described in terms of potential outcomes that it's hard to describe in terms of DAGs. I mean, just think about something like the assumption that there are no defiers in our IV setting. If there are no defiers, then suddenly we get identification. There are, yeah. So I think basically the other point is it's not clear to me what it means to say the graphical framework because there are different graphical frameworks. There's the structural causal model or non-parametric structural equation model with independent errors, and then there are causal Bayesian networks. So, you know, there's more than one graphical framework out there. So yeah, so anyway, so that's my basic answer. My basic answer is you should try to use both, and SWIGs are a way to try to make it easy for people to use both. You know, I think that there are, yeah, I mean, the genesis of this, or one of the reasons I was motivated to come up with this was I teach a course on causal modeling with Michael Hudgens from UNC Biostatistics. We were both, he would teach finite population inference and the Rubin causal model, and I would teach graphs, and people came up afterwards in the break and would say, you know, this was great, we really enjoyed it, but is there any connection between these two approaches? And so this is partly an effort to show that there's a connection between these two. Yes, so Okay, comment about faithfulness. Was it metaphysical? Yeah, so I'm not sure I said. So I mean, it can be viewed in different ways. One way of viewing faithfulness is to view it as, I was viewing it as an assumption. It's an inferential principle, which is to say that, I'm going to think that if there's a constraint that arises, I'm going to bet on, or think it very likely that it arose due to structure rather than due to perfect cancellation. But there are settings where we know that that's not correct. So for example, homeostasis. In homeostasis, it's quite an important property of many organisms, especially mammals, that the external temperature can vary, but their internal body temperature does not vary. Within a reasonable range, doesn't vary so much. That's how homeostasis is maintained. So whenever you have feedback systems, good engineering involves trying to build feedback systems so that certain kinds of external stimuli don't change the underlying state. So there are situations where faithfulness is where there's going to be a mismatch between the conditional independent structure and the underlying causal structure.
You want to? I'm a bit undecided how much we want to keep the queue going right now. So maybe we'll stop this here and take it offline and take a break for 20 minutes until 3:30.
Sounds great.
See everyone back then. Thanks, Thomas. We'll see you in 20 minutes.
Are you willing to answer? Oh, yes, let's start with that.